Hello friends. So today we are going to discuss questions from the year 2021, and they are total of 17 questions, and all these 17 questions are from the mains, and this is part 1 of the year 2021. First question, and it states that consider the diffraction pattern obtained from the sunlight incident on a pinhole of diameter 0.1 millimeter. If the diameter of the pinhole is slightly increased, it will affect the diffraction pattern such that. So we have to choose how the diffraction pattern will be affected if the diameter of the pinhole is increased, and it is increased slightly by a fraction of the amount. So we start from the data which is given to us. First of all, we are given that the diameter of a pinhole let us suppose that is represented as A, then this A will be equal to 0.1 into 10 raised power, I think this is not millimeter. Okay, anyways, that doesn't matter. So this comes as minus 3 meters. And we know that the path difference can be given as path difference, that is our delta of x, is given as a sine of phi, and that is nothing but equal to n times the lambda, that is the integral multiple of the wavelength. Let us call this equation number 1. Here phi is our phase difference and lambda is the wavelength. So you can say our phi is phase difference and lambda is the wavelength. And we also know that the intensity I is also given as 4 times I naught, and we have a cos square of phi. And from equation 1 we can write our sine of phi from equation 1 we have our sine of phi is equal to n times lambda divided by a. So it means if our diameter A is increased, so you can see if our A is increased, and this will be resulting in decrease in our phi. So you can say phi decreases. And if phi decreases, we can say from equation 2 our intensity is going to increase. From equation 2 intensity increases. So it means if we increase the diameter of the pinhole, so you can say that diameter of pinhole is increased, then this results in the size of the you can say the size of the diffraction pattern decreases. Size of diffraction pattern decreases, and the intensity increases. Intensity increases. Therefore, we can say that there is increase in the intensity and the pattern decreases. So size is going to decrease and intensity going to increase. So option number C is the correct one. Option C is correct. Next question. And it states that in a Young's double slit experiment, the width of one of the slit is 3 times the other slit. The amplitude of the light coming from a slit is proportional to the slit width. Find the ratio of the maximum to the minimum intensity in the interference pattern. So in the question itself, it is given that the amplitude is proportional to the slit width. And let us say we have two slit widths. One is our, you can say W1 and another one is W2. And corresponding to W1, we have amplitude A1, and corresponding to W2, we have the amplitude as A2. So we say that our narrow slit width, let us suppose that is our W1, and its corresponding amplitude, let us suppose it is A1, and we have wider slit width, let us suppose that is our W2, and its corresponding amplitude is our A2. But we also know, or rather we can say it is also given in question, that our amplitude is directly proportional to width. So therefore, our width is 3 times the other slit width. So we can say that our W2 is W2 is equal to thrice of W1, or from here we can say our A2 is equal to thrice of A1. And we have to find out the ratio of maximum to minimum intensity on the interface pattern. And we know that maximum is a constructive interference and minimum is a destructive interference. Therefore, with respect to the amplitude, we can write that our maximum amplitude Amax will be equal to A1 plus A2 plus, and A1 is our, you can say A2 is our 3A1, so we can write this as A1 plus 3A1 giving us 4A1, and our minimum is equal to, we have this as A2 minus A1, this comes as thrice A1 minus A1 giving us 2A1, and intensity is directly proportional to the square of amplitude. Intensity is directly proportional to amplitude square. Therefore, we can write that our Imax to I mean will be equal to our A max square and our A min square, and A max is 4A1, so this comes as 4A1 divided by 2A1 and whole square. Here A1 and this goes by 2, giving us 4:1. So option number 3 is the correct one. Option 3 is correct. Next question. We are given that an unpolarized light beam is incident on a polarizer of a polarization experiment, and the intensity of the light beam emerging from the analyzer is measured as 100 lumens. Now, if the analyzer is rotated around the horizontal axis, that is the direction of light, by 30 degree in clockwise direction, the intensity of the emerging light will be dash lumens. So we have a polarizer and a analyzer, and in this case we have to keep in mind that polarizer is the one which is going to give us a you can say variation in the intensity, and the analyzer is just which analyzes the intensity whichever comes into the through it. But the analyzer is also dependent upon the angle with respect to the principal axis. So we can draw this figure, approximate figure, for two parts. In the first, it says that the output measured by the analyzer is 100 lumens, and in this case we can assume that the polarizer and analyzer are parallel. So we can start from there only. So we can say that axis of polarizer and analyzer are parallel. So based on this we can draw an approximate figure. Let us suppose this is the its axis, and we have a polarizer, something like this. So this is our polarizer, and this is our analyzer. And this is our source, which is going to be uniform, and its intensity is I0. So automatically the intensity of the polarizer will be coming as I naught by 2, and if the axes of the polarizer and analyzer are parallel to each other, the intensity that will be outputted by the analyzer will be also equal to I naught by 2. And for this particular question, this I naught 2 for the first case will be equal to 100 lumens. And in the second case, we are given that the analyzer is rotated by an angle of 30 degree. So we can just draw the same figure. So this is our polarizer, and now the analyzer is rotated. So we can just draw, let us suppose this is the rotated somewhere like this. And we have a source which is unpolarized. So once again, this is I naught, it will be I naught by 2, and here the analyzer is rotated through angle of 30 degree, and we can say if the output is given as I1, so this I1 will be equal to I naught by 2 and cos square of 30. So let us call this as case 1, and this is our case 2. So from case 1, we have that our I naught upon 2 is equal to 100. And from case 2, we have that of I1 is equal to I naught by 2, and we have this cos square of 30. I naught by 2 is 100, so we substitute the value, we get our I1 is equal to 100, and 30 is square root 3 by 2 whole square. So this comes as 100, 3, and this comes as 4, and this goes by 25 and giving us 75 lumens. So the output for the second case will be 75 lumens. Next question. It states that in a Young's double slit experiment, two slits are separated by 2 mm and the screen is placed 1 meter away. When a light of wavelength 500 nanometer is used, the fringe separation will be. So this is directly based on the formula of the fringe separation, that is beta, and we know that the fringe separation of, we can say, fringe width or we can say our fringe width, that is our beta, is equal to lambda capital D upon small d. Okay. And here lambda is given to us. Lambda is our, that is wavelength is 500 nanometer. So this will be 5 into 10 to the minus 9 meters. And we have a two slit is separated by 2 millimeter. So we have a small d that is about 2 millimeter. So this becomes 2 into 10 to the power minus 3 meters, and capital D is our 1 meter. 1 meter. So we substitute all these values. We get this as 500 10 to the power minus 9 1, and small d is 2 into 10 to the power minus 3. We get our beta will be equal to, this comes as 250 10 to the power minus 6, and it can be written as 0.25 millimeter. So option number 1 is correct. Option 1 is correct. Next question. It states that two coherent light sources having intensities in the ratio 2x produces an interference pattern. The ratio of I max minus I mean divided by I max plus I mean will be equal to. So we have to find out the ratio of I max minus I mean divided by I max plus I mean. And we already know that if we have two intensities, suppose the intensities are given as I1 and I2, then our I max will be equal to square root of I1 plus square root of I2 whole square, and our I mean will be equal to square root of I1 minus square root of I2 and its whole square. And in the question it is given that the ratio is 2x. Therefore we can say that our I1 upon I2 is equal to our 2x. So we can use directly the formula that our I max upon I mean can say our I max minus I mean divided by I max plus I mean, and I max minus I mean, this will be equal to square root of I1 plus square root of I2 whole square minus square root of I1 minus square root of I2 whole square, and in the denominator we get this as I1 plus I2 whole square plus square root of I1 minus square root of I2 whole square. And we can just open the brackets and we get from here, we get this as I1 square, sorry, there will be not square but because a square root, and this is I2 and plus 2 square root of I1 I2, this will is minus I1, and we have it as minus of I2, and we get this as minus minus will be plus of 2 I1 I2, and the denominator we have the same terms I1 plus I2 plus twice I1 I2 plus I1, and this comes as plus I2 and minus twice I1 times I2. In the numerator, this I1 and I2 cancels out, and in the denominator these two terms cancel out. So we get from here that 4 I1 I2, and this is I1 plus I2 twice, so we can write this as twice I1 plus I2, and 2 goes by, this 4 goes by 2, and we get this as 2 and square root of I1 I2 divided by I1 plus I2. Now the ratio that we know is our I1 upon I2, so we can just remodulate it, and we get this as 2 square root of I1 upon I2, and whole this will be coming as I1 by I2 plus 1, and we have our that I1 by I2 is 2x, so this comes as square root of 2x and divided by 2x plus 1. So the option is 2x square root and 2x plus 1. So option number 4 is the correct one. Option 4 is correct. Next question. It states that if the source of light used in Young's double slit experiment is changed from red to blue, then we have to find out what is going to happen with the fringe and or the central bright fringe, consecutive fringe, as well as the maximum number of maxima on the screen. And we know that the wavelength is changed from red to blue, and we know that our wavelength of, is it red or blue? So here we are going to use two formulas. First is the distance of the nth bright fringe. The distance of nth bright fringe, that is our y of n, is equal to n lambda d upon small d. So from here we can say that our y of n is directly proportional to lambda. Let us call this as first equation, and second, we know that our beta that is our fringe width beta is equal to lambda capital D upon small d, and here also this beta is directly proportional to lambda. Second equation. So here it states that the wavelength is changed from red to blue. In this case, the wavelength is changed from red to blue. Okay, so we can say that wavelength is changed from red to blue. So which basically means that the wavelength of the light is decreased. Wavelength is decreased. Or in simpler terms, we can say that the wavelength of the red is greater than the wavelength of the blue. So using equation 1, we can write that from equation 1, we have y of n is directly proportional to lambda. So it means this y for red is directly proportional to for lambda of red, and y of blue is directly proportional to lambda of blue. And we can just take their ratio and we can write this as y of red upon y of blue will be equal to lambda of red divided by lambda of blue. And from here we can say that the ratio red upon blue is greater than 1. So from here we can say our y of red is greater than y of blue. So it basically means that our consecutive fringes lines come closer. So from here we can say that the consecutive fringes comes closer. And from equation you can say 2, from equation 2 we can say our beta for red is directly proportional to lambda of red, and beta for blue is directly proportional to lambda for blue. So if we take the ratio, we can say our beta for red upon beta for blue will be equal to lambda for red and lambda for blue. So from here we can write that beta for red will be greater than beta for blue. So it means as we shift from red to blue, the fringe width decreases. You can say that as we move from red to blue, we have that our fringe width decreases. Or from here we can say that the number of maxima on the screen increases. Number of maxima on screen increases. So therefore we can say option number C is the correct, you can say correct one, and option number B is also correct one. So B and C are the correct one. Option B and C C are correct. Next question, and it states that in Young's double slit arrangement, slits are separated by a gap of 0.5 millimeter and the screen is placed at a distance of 0.5 meter from them. The distance between the first and the third bright fringe formed when the slits are illuminated by a monochromatic light of 5890 angstrom is. So here we have to find out the distance between the first and the third bright fringe. Means we are talking about the maxima. Okay. And we are given the value of capital D, that is the distance between the slits and the screen. Capital D is given as 0.5 meter, and we are also given as small d, that the gap in the slits is 0.5 millimeter. So we can this as 0.0005 meters. Lambda is also given to us, that the wavelength is 5890 into 10 to the power minus 10 meters. And the distance between the first and third bright fringe we have to find out. So we know that our fringe width, that is beta, is equal to lambda capital D divided by small d. And we can also say that our y will be equal to twice of beta. Therefore, we can write that our y will be equal to 2 lambda capital D divided by small d. We just substitute the values. Lambda is our 5890 10 to the power minus 10. Capital D is our 0.5. Small d is our 0.005. So this gives us that y will be equal to 1178 into 10 to the power minus 6 meters. So this is that, you can say, distance between the first and the third bright fringe. And option number 2 is the correct one. Option 2 is correct. And this can be, here I have directly written this formula, otherwise we can just, you can say, do it in traditional way also. And we are given here that we need between first and third bright fringe. So if this is a screen and this is a center, suppose this is our first bright fringe and its distance is given as y1, and this is our third bright fringe and its distance is given as our y3. So this is our first bright fringe and this is our third bright fringe, and we are supposed to find out this distance, the distance between, that is, we need to find out y3 minus y1. Okay, so in this way also we can easily sort it out. Next question. We are given that the fringe width of 6 millimeter was produced by two slits separated by 1 millimeter apart. The screen is placed 10 meter away. The wavelength of the light used is x nanometer. The value of x to the nearest integer is. So here we are given that the fringe width is produced, that is value of beta is given to us and small d is given to us, and we are given capital D, and we need to find out the lambda. So we can say that our value of beta is given as 6 millimeter. So this becomes 6 into 10 to the power minus 3 meters. And we have small d that is given as 1 millimeter. So this becomes 1 minus 10 raised to the power minus 3 meters. And we have capital D that is given as 10 meters. And we have to find out the lambda. So we know the formula that beta is equal to lambda capital D divided by small d. So from here we write our lambda is equal to beta times small d divided by capital D. And we substitute the values. We get our lambda is equal to beta is our 6 into 10 to the power minus 3, small d is 1 into 10 to the power minus 3, and capital D is our given as 10. So this becomes as 6, and 6 into 10 to the power this will be 6 and 1 5, and we can write this as 6 into, and it is given in nanometer, so we can write this as 600 into 10 to the power minus 9 meters, or we can say this will be over 600 nanometers. So this will be our value of x. So value of x is our 600. Next question. We are given that a galaxy is moving away from the Earth at a speed of 286 km per second. The shift in the wavelength of a red line at 630 nanometer is x times 10 raised to the power minus 10 meters. The value of x to the nearest integer is, taking the value of speed of light, is 3 into, this should be 10 raised to the power 8 meter per second. So here we can use the formula, that is our shift in the wavelength of the red line shift in the wavelength of red line. Suppose that shift is given as delta lambda, then we can say that our v is equal to c, and this is delta lambda upon lambda, and we need to find out our delta lambda. So this becomes delta lambda is equal to v upon c multiplied by lambda, and v and c we know, lambda is also given, so we can directly substitute. We get delta lambda is equal to, we have this as 286, this is 10 to the power 3 meter, and speed of light is 3 into 10 to the power 8, and lambda is our 630 into 10 to the power minus 9. So this gives us 6 into 10 to the power minus 10 meters, and we find out the value of x. So we can say, because it is given as x into 10 to the power minus 10 meters, so 1:1 comparison gives us that value of x is equal to 6. So it will be 6. Next question. This is almost same which we dealt previously also. Only difference is here it is written orange and there it was written as red. So in Young's double slit experiment, if the source of light changes from orange to blue, then the options are also same. And here we know that our fringe width, that is beta, is equal to lambda d upon small d. And from moving from orange to blue, the wavelength is going to decrease. So you can say lambda decreases, therefore the beta also decreases. And if beta decreases, so we can say the distance between the consecutive fringe decreases. So you can say option 2 is the correct one. Next question. It states that in Young's double slit experiment, the distance between the slits varies as time as dt is equal to d naught plus a naught sine omega t, where d naught, omega, a naught are constants. The difference between the largest fringe width and the smallest fringe width obtained over time is given as. So we are given that the distance between the slits varies with respect to this particular equation, and we have to find out the largest fringe width and smallest fringe width. And we already know that the fringe width, that is our beta, that formula is given as lambda times capital D divided by small d. It means if we want a larger fringe width, and it is entirely dependent upon this small d, so from here we can say that our beta will be maximum if we have our small d is our minimum. Or its reverse will be also true. Beta will be minimum when we have our d to be maximum. And we are going to find out thus d minimum and d maximum according to the given equation. So the given equation is that d of t is equal to d naught plus a naught and sine omega t. And depending upon this sine function, d of t will be coming as maximum as well as minimum. So we can say d maximum will be equal to d naught plus a naught, and d minimum will be equal to d naught minus a naught. Therefore, we can say that our beta maximum will be equal to lambda capital D upon this will be our d minimum. Substituting value of d minimum, we get this as lambda d, and d minimum is d naught minus a naught. And our b minimum will be equal to lambda d upon d maximum. This comes as lambda d upon d naught plus a naught. And we need to find out the difference between the largest and the smallest. So we subtract these two terms, we get the difference as B max minus beta minimum will be equal to B max is our lambda d, we can take as common, and this will be coming as 1 upon d naught minus a naught minus 1 upon d naught plus a naught. And we can now easily sort it out. We take as LCM. LCM will be coming as d naught square minus a naught square, and this is our lambda d, and in the numerator we are going to get this as d naught plus a naught minus d naught plus a naught, and here this d naught and d naught cancels out. We get this will be equal to, that is our B max beta max minus beta minimum will be equal to, denominator we had d naught square minus a naught square, and numerator we get this as twice lambda d and times a naught. So this is the difference. So the option number 2 is the correct one. Option 2 is correct. Next question. It says that with what speed should a galaxy move with respect to us so that the sodium D line at 589 nanometer is observed at a 589.6 nanometer. So this is, we can use, you can say, the formula for the Doppler shift, because this is our actual wavelength and this is our observed wavelength. Okay, and we know the relationship between the frequency as well as the, okay, we need to find out speed, so we can just sort it out by using the formula. And for that we know that our f is equal to f naught, and we have the square root of 1 plus, and this will be equal to our this actually will be equal to V upon C, and V upon C is, let us suppose, represented as alpha. So this 1 plus alpha, 1 minus alpha, and here alpha is given as V upon C. And one second, sorry, let me sort it out first. I think I missed one part here. Let me check it. This will be coming as f upon f naught, and one second. It is given the speed Let's start from it basic one. So we have our observed wavelength, original wavelength, that is our lambda, and that is 589 nanometer, and we have observed wavelength, original let us suppose lambda naught, and observed is our lambda, that is our 589.6 nanometer. So from here we can find out a change in wavelength. That is delta lambda will be equal to our lambda minus lambda naught. So we get our delta lambda is equal to, lambda is our 589.6 minus 589, giving us 0.6 nanometers. And we know that the velocity with respect to the change in the wavelength as well as the speed of light, the relationship we already know. So we are going to use that relationship. We can say that velocity v is equal to c multiplied by delta lambda divided by lambda naught, and c we already know is 3 into 10 to the power 8, delta lambda is 0.6 into 10 to the power minus 9, and lambda naught is our 589 into 10 to the power minus 9, and this is now 10 9 goes away, and we get that our velocity v will be approximately equal to 3.06 into 10 to the power 5 meter per second. I think this is okay with respect to, this looks much better. So the observed is 3 into 10 to the power 5 meter per second. Next question, and it states that white light is passed through a double slit and interference is observed on the screen 1.5 meter away. The separation between the slits is 0.3 millimeter. The first violet and red fringes are formed 2 millimeter and 3 millimeter away from the central white fringes. The difference in the wavelength of red and violet light is, so here we are given that we have two, you can say one is over violet and the other one is red, and the distance from the central white fringe is given to us as 2 millimeter, and for the red is given as 3.5 millimeter. Okay, and both are having first, so we have first violet as well as first red fringe. So we are going to use the formula for the position of the bright fringe. So you can say that position of bright fringe position of the nth bright fringe. Let us call this position of the bright fringe nth. We can write that y of n is equal to n lambda capital D upon small d. And in the question we are already given that our capital D is 1.5 meter, small d is given as 0.3 into 10 raised power minus 3 meters, and we have first violet as well as red, so therefore value of n is equal to 1. So therefore we can say for violet and that is our y, let us call it y violet, will be equal to, that is given to us as 2 millimeter. So this is 2 into 10 raised power minus 3 meters, and we use the standard formula, let us call this equation 1. So we can say from 1 we have y of violet is equal to lambda for violet d upon small d, and from here we can write our lambda for violet is equal to y of violet multiplied by small d and divided by capital D, and we can write that our lambda for violet will be equal to 2 into 10 raised power minus 3, and this is small d upon capital D. And similarly we can say for red, we can write y for red is equal to lambda for red, and this is our capital D upon small d. So we get this as lambda for red is equal to y for red multiply by small d and capital D. Y of red we already know, it is given to us as 3.5 millimeter. So this becomes 3.5 into 10 raised power minus 3 multiplied by small d and divided by capital D. And we can easily find out the, okay, we need to find out the difference in the wavelength. So we just subtract their wavelengths. So we can say difference in wavelength, difference in wavelength, that is our delta lambda is equal to lambda for red minus lambda for violet, and we substitute it, we get lambda for red is our d upon small d, we can take as common, and this comes as 3.5 10 raised power minus 3 minus 2 into 10 raised power minus 3, and we substitute the values also. Small d is our 0.3 into 10 raised power minus 3, this comes as 0.3 into 10 raised power minus 3, and capital D is our 1.5 multiplied by, this comes as 0.5 into 10 raised power minus 3, and this 5 goes by 3 and 3 goes with 3. One second. Okay, sorry. This is 3.5, so this comes 1.5. So directly 1.5 goes away, and this comes as 3 into, this will be our 336 and 10 is to the power minus 5, and in terms of nanometer we can write this as 300 nanometers. So we get this as 300 nanometers. Next question, and it states that a galaxy is moving away from the Earth at a speed of 286 km per second. The shift in the wavelength of a red line at 630 nanometer is x into 10 to the power minus 10. The value of x to the nearest integer is, the value of the speed is, this is our 8. And the shift in the wavelength is given as, I think this I already did it. Let me check. I think this I think this I already did. Solved it. Yeah, it is already solved. Okay, so I think I copied it twice. Yeah, so this is already done. So we have to sort it out again. Next question. Okay, so here we are given that in the Young's double slit experiment, the slits are separated by 0.3 millimeter and the screen is 1.5 meter away from the plane of slits. The distance between the fourth bright fringes on both sides of the central bright is 2.4 centimeter. The frequency of the light used is. So here we are given that the distance on the both sides of the fourth bright fringe. So we can just write the data which is given to us. So small d is given to us 0.3 millimeter. So we get this as small d is equal to 0.3 into 10 to the power minus 3. Capital D is given to us 1.5 meter, and we are given the distance between the fourth bright fringe on both sides. Okay, so we can just draw an approximate figure for that, and suppose this is our screen and this is our fourth bright fringe, and this is on the other side, this is also fourth bright fringe, and this distance is given to us as 2.4 centimeters. Okay. And this comes 2 into minus 2 meters, but the formula which we use, that is our y of 4, is only for the one side. So this is our y of 4. So we can say that other side will be also y of 4, and this total comes as 2y of 4. So from here we can write that our 2y of 4 is equal to 2.4 into 10 to the power minus 2. This gives us that y of 4 will be equal to 1.2 into 10 to the power minus 2 meters. So this is the distance of the fourth bright fringe on the one side, that is the top side or bottom side. And we know the standard formula, that is for nth bright fringe, nth bright fringe, we can write our y of n is equal to n lambda capital D divided by small d, and here the value of n is equal to 4. So we can write our y of 4 will be equal to, this comes as 4, and lambda is given, okay, we need to find out frequency, so we are going to find out this lambda multiply by capital D divided by small d. So we get this lambda y of 4 multiply by small d and divided by capital D. We get lambda y of 4 we found out is our 1.2 into 10 to the power minus 2, small d is our 0.3 into 10 to the power minus 3, and capital D is our 1.5, and value of n is our 4. So this comes as 4 times, and this comes as 4 times. So this gives us that our lambda will be equal to 6 into 10 to the power minus 7 meters, and we need to find out the frequency. So we can say, we know that our speed of light, that is c, is equal to lambda times frequency. So you can say our frequency is equal to c upon lambda, and this comes as 3 into 10 to the power 8 divided by 6 into 10 to the power minus 7. So we get our frequency f will be equal to, this is 0.5 and 5 into 10 to the power, this comes as 15, and that will be 14 hertz. And we are given x into 10 to the power 14, so this is equal to x times 10 to the power 14, which gives us that value of x is equal to 5. So the value of x will be equal to 5. Next question. And it states that we are given that a source of light is placed in front of screen. Intensity of the light on the screen is I. Two polarides P1 and P2 are so placed in between the source of light and the screen that the intensity on the screen is I by 2. P2 should be rotated by an angle of dash degrees so that the intensity of the light on the screen comes 3I by 8. So we are given that we have two polarides, so we can divide this into two cases. In case number 1, so we have two polarides P1 and P2. Let us put this is our axis, and we have two polarides this is polaroid 1, and this is polarizer 2, and it is given that intensity that is falling on screen is given as I. So it says the source of light is placed in front of screen and the intensity of light on the screen is I. Okay, so it means we have a source, it is non-polarized, and its intensity is given as I. Okay. So from the first polarizer, so this will be, let us suppose, our I1. So this I1 will be equal to I by 2, and we have second polarizer, let us suppose that is I2, and that is also given as I by 2 if they are, and they are, you can say the axes are parallel with each other. Okay. And this is our case number 1, and for case 2 we can just draw the same figure. So we have two polarizers. This is P1, and now the second polarizer is suppose rotated by an angle of phi, and so output here once again it will be I, and its output is I by 2, and the final output in the second case, in this case let us assume, or in this case it will be same, that is of I1 will be equal to I upon 2, and here let us assume that is I2 prime, that is given to us, it should be equal to 3I by 8, and we need to find out the phi which is to be rotated. So we can use just our case number 2, and we can say that our I2 prime should be equal to our I1, and we have this as cos square of phi, and our I1 is equal to I upon 2, so this comes as I upon 2 cos square of phi, and I2 prime is given to us as 3I by 8. So we substitute, we get this as 3I by 8 is equal to I by 2, and this comes as cos square of phi. Here I and 8 goes by 4, so we get that cos of phi will be equal to square root of 3 divided by 2, and this gives us that our phi will be equal to 30 degree. So we have our phi is equal to 30 degree. Next question. And it states that the light waves from two coherent sources have same intensity I1, I2 is equal to I0. In interference pattern, the intensity of the light at minima is 0. What will be the intensity of the light at maximum? So here we are given that the minima is equal to 0. So we can say our I minima is equal to 0, and we also know that our I minima in terms of I1 and I2, we can write that as square root of I1 minus square root of I2, and this comes as whole square. And our I max, we can write that as square root of I1 plus square root of I2, and its whole square. And I minima is our 0, and we are given that I1 is equal to I2 is equal to I naught. So we can easily substitute value of I1 and I2 as I naught, and we can write that our I max will be equal to our I naught plus square root of I naught and square. So this comes as 2 I naught whole square. So we get our I max will be equal to, this comes as 4 times I naught. So option number 4 is correct. 4 is correct. Next question. And okay, in double slit experiment, the width of one of the slit is 3 times the other. The amplitude of the light coming from the slit is proportional to the slit width. Find the ratio of maximum to minimum intensity in the interference pattern is x is to 4. Find the value of x. So we are given that two slits, the width of one slit is 3 times the other, and we also know that intensity is directly proportional to the square of the amplitude, and our width is directly proportional to the amplitude. And so if we have two intensities I1 and I2, so you can say for intensities I1 and I2, and if we have two slit width, so we can say narrow slit width, let us suppose as W1, and broader slit width, let us suppose is our W2. So we can say that our W2 will be equal to 3 times W1. So, and here amplitude, let us suppose given as A1, and here the amplitude is, let us suppose, given as A2. So therefore we can write that our A2 is equal to 3 times A1. And we also wrote that our intensity is directly proportional to amplitude square. Okay. So we can say that our I1 to I2 will be equal to our A1 upon A2 and its whole square. And we know that our A1 is equal to thrice A2 whole square, and we have our A2 and A2 cancel out, so this comes as 9. Okay, I have written this reverse, let me correct it. So this comes as 1 and 2, and this is also 1 and 2. Yeah. And the ratio of maximum and minimum intensities, we have our I max upon I mean, that will be equal to square root of, we have to find out maximum to minimum. Okay, so we get this as I max is I1 plus I2 whole square, and we have this is square root of I1 minus I2 whole square. So we can easily write it as, if we take I2 as common, I2 cancels out, this comes as I1 by I2, and I1 by I2 is nothing but our square root of 9 plus 1, and here comes as square root of 9 minus 1, and this will be our whole square. So we get this as 3 plus 1 is 4, and this is 3 minus 1 is our 2 whole square, and 4 goes by 2, so this will be equal to 4:1. Maximum to minimum is x:4. Doesn't look like. Maximum to minimum is find the ratio of maximum to minimum. I think it should be reverse. Minimum to maximum. Yeah, I think so. Otherwise it won't match. So this should be our I minimum to I maximum will be equal to 1 by 4, which is our x by 4, giving us value of x is equal to 1. So I think there is some problem here. Ratio of minimum to maximum. So then it comes x by 4. Otherwise it won't match. So value of x will be equal to 1. Next question. Oh, so these were all the questions. So this completes the part 1 of the year 2021, and in this part 1 we solved total of 17 questions, and all the questions from the mains only. So next part, in the part 2, we will try to cover some other questions also from 2021. That can be a combination of mains as well as advanced, or depends upon the number of the question, or it will be only mains, and if required we will move to the third part also. So this completes all the questions. Thank you.